Good evening, guys. So today we are going to do this part, geometrical isomers and optical isomers. How to calculate them in the examination point of view. So the way of calculating is majority are going to do a silly mistakes. That's why, children, we are going to do this part, very important part. This is also one of the corner which covers 4 marks. So listen, Baba. The geometrical isomerism, which is related with the double bonded carbon, that's going to be related with what's called here double bonded carbon attached with the different groups here, children. Suppose I'll take one of the compound here, children. Let it be the double bond may be even or odd. If the two terminals are going to be different groups, if the two terminals are going to be the different groups, then the total number of geometrical isomers is equals to 2 to the power n. The n is going to be number of double bonds. The n is going to be number of double bonds. So, Baba, here, this is a compound. One terminal is methyl, the other terminal is bromine. Then it's going to be 2 to the power 3 or nothing but geometrical isomers, 8 GI isomers. 8 GI isomers. So this is the first case, children. One of the best question from this you can take. Coming to the second one, Baba, here. So when the two terminals are same with even number of double bonds, when two terminals are same with the even number of double bonds, then we should calculate the possible geometrical isomers, 2 to the power n minus 1 plus 2 to the power p minus 1. So here p is equals to n by 2. Once again I am repeating, Baba, here. When the terminals are going to be same, then the compound with even number of double bonds, which is going to be calculated in this way. The total number of geometrical isomers can be calculated by this way. That's going to be 2 to the power n minus 1, 2 to the power p minus 1. In this case, p is going to be, just for notation's sake, p is equals to n by 2, Baba. P is equals to n by 2. So now we will calculate this one. What's the possibility of this one? 2 to the power n minus 1 means it's going to be 2 to the power 2 minus 1, 2 to the power 1, 2 to the power p minus 1. This is 2 by 2. That's going to be 2 by 2 means 1 minus 1, 0. That's going to be 0. Something to the power 0 is 1. Therefore, the total isomers are going to be 3. The total isomers are going to be 3. Got it, children? So, after that, when the same case number 3 we are doing, what's called here case number 3 is going to be here. See, the terminals are going to be same, but the number of double bonds are going to be odd. When the number of double bonds are going to be odd, the P is going to be calculated n plus 1 by 2. N is here 3, odd number of double bonds. Let's calculate the number of geometrical isomers. 2 to the power 3 minus 1, 2 to the power 2, 2 to the power, here we will do this, children. 2 to the power, whatever is called here, p is equals to 4 by 2. So that's, children, 2 to the power 2 minus 1. So that total number of 4 plus 1, 4 plus 2, 6 GI isomers. This is the case, children. So what we have done is going to be, once again I am recollecting you, children. So case 1, when terminals are not equal, then the number of geometrical isomers are calculated by this principle 2 to the power n. N is going to be number of double bonds, Baba, here. When the terminals are going to be same, the formula to be used is total number of geometrical isomers 2 to the power n minus 1 plus 2 to the power p minus 1. In this case, if n is even, p stands for n by 2. Then based on that, the possibility is for 3 geometrical isomers here. If case 3 we have taken, if n is odd and when the terminals are going to be same, when the terminals are going to be same here, children. So this is the case 2. In both cases, terminals are going to be same. when n is odd, p is equals to n plus 1 by 2. 2 to the power 2, 2 to the power 2 minus 1. The total geometrical isomers are going to be what's called here 6. Are you clear, children? So after that, we will go for optical isomerism. You are all familiar with the optical isomerism, children. What's that optical isomerism which we are going to see here means? See, it's based on, the optical isomerism is shown by the compound, it should have at least one chiral center. So that is going to rotate the PPL, plane polarized light, in clockwise and anti-clockwise direction. That gives rise to dextro and levo isomers. See here, children, in the first case, we are going to see the two terminals are going to be different in this case, and whenever the n is equals to what here, whatever it might be, the two terminals are different. When the two terminals are different, then the formula, see here, children, as it is like geometrical, 2 to the power n. So that Baba, here how many chiral centers are possible? 2, 3, 4. So that's why the total number of isomers are going to be 2 to the power 4. So it's overall 16 isomers are possible. Total isomers are going to be 16. Meso isomers are going to be 0. Meso are going to be 0. And after that, what is meso? In this session only I will finish, Baba, here. And after that, case 2 we are taking. What's that case 2, Baba, here? Let us verify this. See, if the terminals are going to be same, but whatever the chiral centers are going to be even. When the chiral centers are going to be even, n is equals to even. What is happening? Let us see here. Optically isomers are going to be here 2 to the power n minus 1 and 2 to the power n by 2 minus 1, as it is in this way. As it is in this way. Then we can calculate, no, how we are going to calculate, Baba, here? N is equals to, how many are possible? 2 to the power 4 minus 1 plus 2 to the power 4 by 2 minus 1, that's equivalent to 2 to the power 3 plus 2 to the power 1. So that it's going to be 8 plus 2, 10 isomers are possible, Baba, here, 10 isomers. But meso are going to be only 2, meso are going to be 2 here. So meso means optically inactive one, that's called, which is having plane of symmetry, children. Once again, the case 2 is going to be when the terminals are same with the even number of double bonds, it resembles as it is that geometrical isomers. The total possible isomers are 2 to the power n minus 1, 2 to the power n by 2 minus 1, like geometrical isomers, right? So it's very easy to remember, children, in this comparison, in this comparing both of them, geometrical and isomer, because it's almost all memory based, children. So now coming to this, whatever we have done, case 1 and case 2, different terminals, same terminals with even number of double bonds. Coming to this, case 3 is concerned. When you have done is going to be case 3. What's that case 3 here, children? Terminals are going to be same, no doubt in that, but coming to that, the number of chiral centers are going to be odd. The number of chiral centers are going to be odd here, children. So when the number of chiral centers are going to be odd, let us verify this, children. Compare these two also. Whenever n is odd, see, the formula is going to be 2 to the power n minus 1 minus 2 to the power n minus 1 by 2. Coming to that, total isomers are going to be 2 to the power n minus 1. For instance, children, let's hope this. Whatever that we will do in this way by taking the formula itself. So how many are there, Baba, here? Optically active isomers are 2 to the power 3 minus 1 means it's going to be 2 to the power 2 minus 2 to the power 3 minus 1 by 2. That's going to be 2 to the power 1. And meso isomers are going to be, that's called 2 3 minus 1, 2 to the power 1. Now, let's verify this. 4 minus 2, it's going to be 4 minus 2 means 2 optically active isomers possible. And how many isomers are possible? 2 mesoisomers are going to be possible here. The total number of isomers are going to be 4. The total number of isomers are going to be 4 here. Optically active 2, and this is going to be 2 also. But see here children, you can apply this, you are also getting same number. O, A plus M is equals to 2 plus 2. It's going to be 4 isomers children. So this is about what's called here the cases where we have done the way of calculating optically active isomers with different terminals, with the same terminals, odd, even number of double bonds, odd number of double bonds. Similar way, geometrical isomers also, Baba, it's going to be different terminals, same terminals, even double bonds, odd double bonds. 100% you should practice these two children. So that's going to be the case is concerned, right? Thank you very much children.